That's disgusting. All right, it is 6 o'clock by my watch, so we're going to go ahead and get started. I'm going to start with a few of the homework problems from section 1.2 through 1.4. All right, let's get into this. 1.4 was easily the most challenging section that I saw in this group. So let's start off with number 9. I think number 9 was the same for everyone. So let's look at that one. Number 9 in the section 1.4 WebAssign homework asked you to simplify b over a minus a over b all over 1 over a minus 1 over b. This is an example of a complex fraction where we have, or I call them nested fractions, where we have little fractions going on inside of big fractions. I'm going to go ahead and do this particular problem using a similar strategy to what they use in the videos. When I did a compound fraction problem in class, I did it a more challenging way, I guess, so that we could practice adding rational expressions and dividing them and all that jazz. That was the worst, not the worst, but I guess there's two strategies, and the one that we did in class wasn't the right one. I mean, it's not wrong, but it wasn't the best one. There we go. It wasn't the best. The best strategy here, in my opinion, is to find a common denominator, and it's best if you can find a least common denominator. In this case, the least common denominator of all of the fractions. I got 4 different fractions here. The least common denominator of all the fractions is a times b. And so we're going to multiply on top and bottom by that least common denominator. Now, if a times b is just, or sorry, a times b divided by a times b is just 1. So we're not really changing anything. We're just changing the way that it looks. And so when I multiply on top, I want to make sure I distribute. And same thing on the bottom. We're going to distribute through on the bottom. Okay? So on top, when I distribute on the first term, it's b over a times ab. When I distribute onto the second term, it's a over b times ab. On the bottom, it's 1 over a times ab minus 1 over b times ab. Now, just looking at this first term in the numerator real quick, and I'll do the other ones. Well, we're gonna do this one slowly and then do the other ones more quickly. If I look at b over a times ab, that's the same as multiplying it by ab over 1. And when you multiply fractions, this ends up being ab squared on top. When I multiply across the top, on the bottom, a times 1 is just a. And then I have my numerator written as a product. My denominator is a product. It's a product of one thing. But the point here is I have both my numerator and my denominator written as a product, and they share a common factor, a. And so I can cancel the a. And I'm just left with b squared. Again, that was just that first term. All right. So this first term here, all that's left is b squared. In a similar fashion, Actually, the way that you would probably look at it is just up here. You would say, okay, the b's cancel there. I'll have a times a, which leaves me with a squared. In the denominator, in the first bit, I have some a's that cancel. In the second bit, I have some b's that cancel. And after the cancellations there, we're left with b minus a. Okay, so we've cleaned this up pretty nicely. We can continue simplifying here, noticing that my numerator is a difference of squares. Okay, so we're going to factor it as a difference of squares. B squared minus a squared factors into b minus a times b plus a. And now once again, I have my numerator written as a product of two terms, b minus a times b plus a, and my denominator is a product of just one term. And my numerator and my denominator share a common term, so I can go ahead and cancel that term, and all that's left is b plus a. Okay, now there's a similar, question 10 is a similar idea. I'm not going to go through question 10, but the idea there is similar. I will go ahead and go through at least my version of question number 11 from the same homework. It looks like 7 over x plus 1. Sorry, this is number 11 from the 1.4 homework. 7 over x plus 1 plus 8x over x plus 3. That's my numerator. And the denominator, x over x plus 1 plus 7 over x plus 3. And we're going to employ a similar strategy here to simplify this. Again, the instructions are just simplify. So not really, we're not really doing anything. We're not changing the meaning of the expression. Well, we kind of are, but let's not worry about that. We're changing the domain. In the process of doing this, we're changing the domain. But other than that, we're not changing the meaning of the expression. We're just changing the way that it looks. Okay? So we're going to use the same strategy. In this case, our least common denominator is, of all the denominators, we have x plus 1 and an x plus 3 and another x plus 1, another x plus 3. The least common denominator of all the denominators is x plus 1 times x plus 3. So we're going to multiply by x plus 1 times x plus 3 on top and bottom. Now here, this is an example of, we have this strategy that doesn't necessarily exactly follow from what we know about simplifying fractions, but this is the quicker strategy. It's the quicker, more efficient strategy. Now we're going to do, it's going to work out exactly the same way as the last one. We're going to distribute. When we multiply we got two fractions that we're multiplying together, and so we're going to multiply across the top, which involves, I guess if you want to think about, hey, there's some parentheses here, and we need to distribute across the parentheses. Okay? Same thing on the bottom. We're going to distribute across the bottom onto both these terms. And when I distribute across the top, I have 7 over x plus 1 times x plus 1 times x plus 3 plus 8x over x plus 3 times x plus 1 times x plus 3. When I distribute in the denominator, I have x over x plus 1 times x plus 1 times x plus 3 plus 7 over x plus 3 times x plus 1 times x plus 3. Now there's lots of cancellation. We're just going to go ahead and do this all here. I can cancel x plus 1's here. I can cancel x plus 3's here. I can cancel x plus 1's there. and x plus 3's there. All right, so there's a cancellation. We have 7 times x plus 3 plus 8x times x plus 1 all over x times x plus 3 plus 7 times x plus 1. And we can continue to simplify. I'll go ahead and get rid of the parentheses. When I distribute the 7 through, I have 7x plus 21 there. When I distribute the 8x through, I have plus 8x squared plus 8x. On the bottom, we end up with x squared plus 3x. When I multiply out the first bit, and then 7x plus 7 when I multiply out the second bit. They were nice here and didn't give us any wonky fractions. Let's see, I can combine like terms on top and bottom. On top I have 8x squared plus 15x plus 21. On bottom we have x squared plus 10x plus 7. Okay. Now I don't think, neither the top nor the bottom is gonna factor any further. They're both prime quadratics over the integers, and so this will be my final answer here. Okay, so those were a couple examples where we were working with complex rational expressions or complex fractional expressions. You guys did, oh, sorry, there was one more from 1.4 I want to do. I made a video about these, but I guess the video didn't have enough examples like the homework problem, and so we are going to, this is like the last problem. I don't even know what the number of it is. Like last problem in the 1.4 homework. So it'd be simplify 6x minus 5 cubed times 2 times x squared plus 4 plus, oh, sorry, there's supposed to be a 2x at the end there, I think. Yeah. I left that part out. Times 2x plus x squared plus 4 squared times 3 times 6x minus 5 squared times 6. All right, so the idea here is that we have a sum of two expressions. There's this expression and this expression, and we're adding them together, okay? And so whenever you see like polynomial stuff or algebraic expressions where there's clumps of multiplication separated by addition and subtraction signs, you want to think of the clumps of multiplication as being a single expression, okay? And then within that expression there are factors. And the idea here is that we're going to factor out the common factors. Now, focusing on the constant terms, I'm going to write 6 as 2 times 3. Both of these expressions have a 2. All right, this expression has 2 2's, and this expression has 1 2. But since they both have at least a 2, I can factor out a 2, but the most I can factor out is a single 2. Okay, now after factoring out a single 2, I'm going to, I guess, pull that one out, and that's the only option I have there. All right, so from a constant perspective, the only thing that we can factor out is a 2. Now, the first term has some 6x minus 5's, and the second bunch has some 6x minus 5's. The first bunch has 3 of those, and the second bunch has 2 of those. So I can factor out 2 of them. I can factor out a 6x minus 5 squared. Okay? And when I'm done, when I've factored that out, well, I've taken 2 of these 3, so there's 1 left. And I've taken both of those, so there's none left there. Now, I'm not necessarily... it looks like I'm canceling things here, and I can see why it looks like that. But I'm not necessarily canceling things here. I'm just keeping track of what I've factored out. Okay? I didn't necessarily cancel... like I'm not canceling this 2. I'm just keeping track of the fact that I factored it out when I come down here. Okay? All right. Now, the last thing that these two expressions have in common is some x squared minus 4. The first version has 1 of them, and the second version has 2, or the second expression has 2. So I can factor out one copy of x squared plus 4. And when I do that, well, both of those have been, or sorry, that one's been factored out, and then from those 2, I'm left with 1. Okay. So now that's all I can factor out. What I'm left with is, from the first expression, I have a 6x minus 5 still sitting there, and a 2x. From the second expression, maybe I should put these in brackets. From the second expression, I have an x squared plus 4 factor left. I've got this 3. And I've got that 3. And we can go ahead now and simplify inside the brackets. So I got 2 times 6x minus 5 squared times x squared plus 4 times, when I distribute the 2x through, I have 12x squared minus 10x. And then in the second expression, when I do 3 times 3 is 9, and then distribute that through, I have 9x squared plus 36. And we can now combine like terms inside the brackets. I have a 12x squared plus a 9x squared leaves me with 21x squared minus 10x plus 36. And I think that's most of the hard work. Once again, yeah, this polynomial here does not factor, nor does this one, nor does x squared plus 4. Both of those are prime quadratics over the integers. So neither of those factors. And so we're done factoring now. We're done factoring now. And that'll be our simplified answer. And I think I mentioned this in the video, but this kind of factoring problem shows up. It's a pretty common factoring problem in a calculus course. Okay, I mean, I can tell you exactly where this problem came from, but it wouldn't likely have the explanation wouldn't be meaningful to someone who hasn't taken the first few weeks of a calculus course. All right, I think I have time to do one more problem. Or maybe I have time to do a couple of factoring problems. You guys did really well with the factoring, but just we have time to do it, so let's go ahead and do it. The first one I want to do, I can't remember what this problem was, what number this was in the 1.3 homework. X to the fourth minus 9x squared. So remember, I told you guys in class, like the first thing you want to look for is some common factors, GCFs. In this case, x squared is a common factor of both of those terms. I got 2 terms. Now, I mean, I got 2 terms in this problem the same as I had in the last problem. It's just that the terms are simpler. Anyways, I'll factor out an x squared, and I'm left with x squared minus 9. And then x squared minus 9 is a difference of squares. So that will, remember, difference of squares. If I have a squared minus b squared, that factors into, I might as well just erase the whole thing. If I have a squared minus b squared, that factors into a minus b times a plus b. That's a factoring formula that you're meant to have fairly well, you're supposed to have that down. So I guess if I wanted to write this as x squared minus 3 squared to make it more explicit, all right, x is playing the role of a and 3 is playing the role of b, so I have x minus 3 times x plus 3. Okay, so that's this degree 4 polynomial completely factored. And then one where we can practice our sum of cubes, factor 27x cubed plus 64. So the sum of cubes formula, a cubed plus b cubed. I think I showed you guys this the other night, the SOAP thing. Regardless whether it's a sum or difference of cubes, I have a binomial with an a term and a b term, and then a trinomial with an a squared term, an ab term, and a b squared term. The first plus or minus is the same as what you started with. The second one is the opposite, and the third one is always positive, always plus. Okay? Now, before I can dig into using the difference of cubes formula, it might be helpful to write these terms. Again, we have two terms here. Write the terms as things that are cubed. Now, 27x cubed is 3x cubed. So 3x is playing the role of a. And 64 is 4 cubed. So 4 is playing the role of b. I think I told you guys in class that we want to be able to recognize some of these perfect cubes and perfect fourth powers and things like that in order to mostly be able to do the difference of cubes formula, but there's some other reasons too. Anyways, now that I've identified my a and my b, now if you have to identify these things more explicitly, like say, hey, 3x is playing the role of a and 4 is playing the role of b, so that you can plug the right things into this formula and take it slowly. I got a plus b, that's 3x plus 4. That part's easy enough. Then a squared would be 3x squared minus a times b is 3x times 4 plus b squared is 4 squared. And then simplify. 3x plus 4, at least in the second batch of parentheses. 3x squared is 9x squared. 3x times 4 is 12x, and 4 squared is 16. You gotta find your own pace. Find your own pace and go at your own pace with these problems. Okay, so those are all the examples that I have to go through from the homework. We're not always going to have time to go through homework problems, but we did this week, so I decided to do some. In general, if you have homework, if you have questions from the previous week's lesson or from the previous week's homework, you can always ask, and the worst I can tell you is, hey, we don't have time for that. All right, now on the subject of the first few sections from, or I guess the first few sections were the homework. Our first quiz is coming up next week. It is going to be it's going to cover sections 1.2 through 1.4. So let me go back here. All right, so quiz 1 is next week. We'll probably take it roughly first thing. You should assume that we're going to start the quiz right at 6. Okay? We're not necessarily going to start it right at 6, but you should assume that we're going to start it right at 6, because just going to depend on what kind of time we have. It's going to be a 25-minute quiz. All of our quizzes are 25 minutes, I think. I'm pretty sure all of our quizzes are 25 minutes long. On this particular quiz, there's going to be 6 problems that are similar to the problems on your WebAssign homework. You're not going to be allowed to use any notes or scratch paper. a lot of students, or not a lot, some students have difficulty getting things written down in the space allowed, and they want to use scratch paper. There's no scratch paper in this class. Okay, so get used to writing in the space allowed. Okay, now I said that these 6 problems are similar to homework problems. If you want an even better idea of the kinds of problems that your quiz problems are similar to, there is a practice quiz available in the reviews. If you scroll down to on the bottom of our homepage and click on reviews, there is a practice quiz here. Okay, a practice quiz with, in this case, the practice quiz has 10 different problems on it. Your quiz problems are the same as these practice problems with different numbers. Like, I cannot emphasize how, I guess it's one of those things where I think I told you guys most of my experience is teaching at the calculus level. And at that level, they might give study guides that tell you the kinds of problems. But I hear a common gripe that the exam was nothing like the practice test or whatever. Our quizzes and exams are exactly like the practice. Okay? And I say exactly, I mean exactly. And if we have different definitions of exactly, then you have to adjust to mine. But I would say that our quiz is exactly like this practice quiz. Okay. Now the answers are given. So you have this practice quiz, and the answers are given. Also, on this review page that we click through to, there is an exam review, and the exam review has some similar problems on it. Actually, there's 2 versions of each exam review. So there are similar problems on the, for example, Exam 1A review. Now, the Exam 1A review has a lot more other kinds of problems, but the first few problems here are similar to the ones that you guys have on your quiz and on the practice quiz. And the A version of the exam review not only has answers, but has solutions. So we talked briefly last week about what kinds of work we would expect you guys to show on quizzes and exams. You can look at the written solutions for the exam review to see what kind of work is sufficient. Okay? Also, if you go to the Math 136 YouTube channel, they have videos. They have videos where they're working through the exam review. So you have resources for the kinds of problems that you're going to see on the quiz, as well as how to write solutions to these kinds of problems as well. Okay? So with all that said, your next opportunity to earn Instructor's Choice points is to, let's see, Practice Quiz 1. Yeah, write complete solutions to Practice Quiz number 1 to be turned in prior to the quiz. There's going to be an announcement going out here either tonight or sometime tomorrow, early day. Guidelines, is this up there yet? Yes, it's not. That announcement hasn't gone out yet, but the announcement, the guidelines for written solutions and practice quizzes and exam reviews, you'll be able to read that on Ivy Learn pretty soon. Again, it's going to be an announcement that comes out sometime in the next 24 hours. So yeah, quiz next week. Write up solutions to the practice quiz for Instructor Choice points. I can't overemphasize how important the practice quizzes and exam reviews are in this course. These reviews and this practice material is exactly like the assessments. The fact that those are worth so much towards your grade, you really want to take those seriously. Okay? So, in addition to the web assign homework that you guys have due, I think the next batch of web assign. Oh, I guess you guys are on a different schedule because of the holiday. But anyways, in addition to the web assign homework, you have the practice quiz also to work on over the next week. All right. If anybody has any questions about the quiz, please feel free to send me a message, and I'll be happy to answer what I can. All right. Now we're ready then to move on to the main topics for the evening. The first is section 2.1. So hopefully you watched the Math 136 YouTube channel videos over section 2.1. Section 2.1 is on equations. And I guess more specifically, it's about solving equations. Okay? Now, some terminology that I want to bring up. This box is in your e-text. I guess I can move over here now. Actually, both of these boxes are in your e-text. So that we're all clear on the meaning of words. It's surprising to me how many people don't know what an equation is. An equation, here they specifically say an equation in X is a statement of equality involving one variable. Okay. Now, in general, an equation is just a statement of equality. So there's two things there that I want to mention. An equation has an equal sign. Okay. Like in their illustration here, x minus 5 is equal to 4x. There is an equal sign. The x minus 5, that's not an equation, that's an expression. We call that an algebraic expression. There are other terms that we could use for x squared minus 5, but equation is not one of them. It's not an equation because it doesn't have an equal sign. Same thing for the 4x. The 4x I would call an expression or a term. Okay? The other thing I want to mention here is the word statement. This is a mathematical sentence. It's got a subject and a verb is equal to and a direct object for x. Okay. Now I think I didn't learn it this way when I was first learning algebra, but sometimes they say that like make x the subject is a description for a process. But anyways, it is a statement. It is a sentence. When you read it out loud, it's a mathematical sentence. It's saying something. Okay? That's what an equation is. Another bit of terminology that's used kind of loosely and incorrectly a lot of times is solution. Okay, a solution to an equation. Now the term solution is used differently in different contexts. When I tell you guys to write solutions to math problems, that basically means, you know, show me the answer and all the work required to get that answer. In the context of an equation, when you're asked to solve an equation, I guess that's the last one here. Solve an equation means find all the solutions, and to find a solution to an equation, well, that's just a number that makes the equation true. Okay, so x squared minus 5 is equal to 4x. Yeah, that's a statement, but it doesn't have like a truth value. It's neither true nor false. Most English sentences are either true or false. Now, when I write the sentence, my brother is tall, that's an English sentence. It's a statement about my brother, and it's a true sentence. At least I think it is. I guess part of this requires that we're all on the same page with regard to tall. My brother's, I think, like 6'2" or 6'3". He's a little bit shorter than me, but he's still, I think, what almost everybody would consider tall. Okay? So my brother is tall is a true statement, but that's only because I'm saying it. Okay? If somebody else says the sentence, my brother is tall, it may not be true, or it may not be even meaningful. Some people don't have brothers. Okay? So for someone who doesn't have a brother, them saying my brother is tall, I don't even know that that's a meaningful statement. But anyways, I guess my point here is that, all right, we have English sentences whose truth value depends on who is saying it. And if you want to think the same thing about our variable sentences, you can think of the variable x is saying, if you take me and square me and then subtract 5 from me, that's the same as if you multiply me by 4. And depending on which variable is saying that sentence might be true or might be false. For the variables for which that is a true statement, we're going to call those solutions. And if you plug in a number and the equation is not true, then it's not a solution. Okay? So that's what a solution to an equation is. All right? The number b satisfies an equation means the same thing as b is a solution. So it's just different terminology for the textbook says solution, root of an equation, variable or number satisfies an equation. Those are all roughly the same thing. And then also there's this notion of equivalent equations that I think is really, it's one of these things that's kind of floating under the surface. You're doing it all the time, but you don't realize that you're doing it, okay? So they have an example here. The equation 2x plus 1 is equal to 7 is equivalent to the equation 2x is equal to 7 minus 1. Their definition here, by the way, equations are equivalent if they have the same solution. I think if it were me, I would add and the same domain. I think that's important. Equations that have the same solutions and the same domain are equivalent. But that's just my personal opinion. Anyways, all four of these equations, there's 4 equations, and they're all equivalent. They all have the same solutions. Now, you might recognize this as, okay, they're solving this equation, okay? All right, all right, in the first step here, they just subtracted 1 from both sides. And then the second step, they just 7 minus 1. Here's an equation. 7 minus 1 is equal to 6. That's an equation that's always true. At least once we give meaning, this is going to be, once we give meaning to 7 and 1, the numerals 7, 1, 6, and minus, okay? There are a lot of, and equals. I mean, every single symbol in this expression has to be given meaning in order for it to be true. But anyways, that's going to be one that we're going to say is always true. We're going to always have agreement about the meaning of those symbols. And then moving here from the third equation to the fourth, we've just divided on both sides by 2. And so these equations are equivalent. We'll talk, we'll spend a little bit more time talking about equivalent equations here in the context of an example in just a second. And the very last one is easy to see what the solution is. If I plug in 3 over here, 3 is equal to 3 is a true statement, and so on. So 3 is a solution to this last equation. It's easy to identify the solutions to the last equation. Okay? Now, most of this section is devoted to finding solutions to linear equations. Okay? And those are equations that can be written as ax plus b is equal to 0. They can be. Keyword is can be. You're not always have to write them explicitly that way, but the point is that they can be. Or another way of saying it is, all right, there is an equation of this form that is equivalent to the one that you start out with. Okay? And the process for finding solutions, again, solving here is a process. This is a process. Sorry. Yeah, well, it's not a process. That's exactly the opposite of what I'm trying to say here. Solving is a goal. There's a goal here. The goal here is to find all the solutions. It's not necessarily a process. Okay? Some solving can be done without doing a process. Okay? Solving an equation is a goal, and the process that you use to accomplish that goal is going to be different depending on what kind of equation. And so that's where it's going to be important for us to identify what kind of equation that we're looking at. For a linear equation, the process of solving is typically, I would call isolate x. I would call it isolate x, which means get x on one side and get numbers on the other side. Okay? Isolate x. So, an example. Let's go ahead and do an example here. Now this is going to be one that's a little bit more challenging than some of the ones that they showed in the video. But there's a reason. So x plus 9/2 times 2/3 x minus 1/2 is equal to 2/3 x squared plus 1/6. All right, so there's an equation. There's a statement of equality, an equation in the variable x. Oops. All right, now we're going to find some equivalent equivalent equations here. Okay, so we're going to talk about some operations that preserve. We want to preserve equivalence. And then hopefully we can whittle this down to something where we can just easily identify the solution or solutions. Now, I don't like these fractions, and I'm guessing you guys probably don't either. Okay? The nice thing about fractions is if you have an equation, you don't ever have to mess with fractions. You can always get rid of all of the fractions. Now, if I were able to multiply through by 2 here, I could kill that 9 halves. And if I multiply through by 6 here, I could kill the 3 and the 2 there. Okay? So I'd like to be able to multiply this factor by 2 and this factor by 6. That 6 is sitting in a really awkward spot. I'm going to give myself enough space where I can write that 6 in a less awkward spot. So we started off with x plus 9 halves times that. Again, I want to multiply through by 2 here to kill off the halves and the 9 halves. And I want to multiply by 6 here so I can cancel the 3 and the 2. So think about it as finding common denominators in each term. Okay, my least common denominator in this term is 6, and my least common denominator in this term is 2. And then my least common denominator in this term is 6. Now, I've been throwing in a bunch of numbers. I took my original equation and I added a bunch of numbers. If I want to maintain the equivalence of the equation, I have to multiply by the same number on both sides. In this case, if I multiply by 12 on both sides, I have equivalent equations, and I accomplish the task of killing off all the fractions. Okay? Now, if you don't like this task of killing the fractions, you can just work with the fractions. Be my guest. Okay? But I think killing off the fractions is not too incredibly challenging, and it's something that most students prefer not to work with fractions. Most teachers, I prefer to not have to work with fractions. It's just easier. Okay? Anyways, when I distribute the 2 through here, I have 2x. Ooh, I want to switch back to black. I have 2x plus 9. When I distribute the 6 through, this, if you need to take more steps to see this, when I distribute the 6 through, I have 4x minus 3. Here, when I distribute the 12 through, you get 8x squared plus 2. When I FOIL out the left-hand side, we have 8x squared minus 6x plus 36x minus 27. By the way, let's see. In terms of preserving equivalence of equations, we had our original equation, and then we multiplied on both sides by the same number. Actually, you can multiply. I guess one way to preserve equivalence of equations is to multiply on both sides of the equation by the same number that's not 0. Okay, we're not going to see it in the context of this problem, but dividing on both sides by the same non-zero number also preserves equivalence. Doing basic algebra on one or both sides of the equation produces an equivalent equation. So I guess moving from here to here, we just FOILed out. That's basic algebra. Okay. Combining like terms is another example. So I got 8x plus 30x minus 27 is equal to 8x squared. So again, basic algebra. Doing basic algebra on one side or the other of an equation preserves the equivalence. I can add and subtract things from both sides. Okay? So in this case, I'm just going to subtract. Oh, this is a bad way to put it. I'm going to subtract 8x squared plus 2 from both sides. And I get, all right, 8x squared minus 8x squared plus 30x. Getting a little bit sloppy. Minus 27 minus 2 is equal to 0. When I subtract, again, subtract 8x squared plus 2 from both sides, you can add or subtract on both sides of an expression by the same expression, or as long as it's not, well, I guess even if you add or subtract 0, that's fine too. Okay? You can add or subtract any number from both sides of an equation and get an equivalent equation. And when I simplify by combining like terms, I get 0x squared plus 30x minus 29 is equal to 0. Again, adding on both sides of an equation preserves equivalence. So 30x is equal to 29. And then dividing, I guess we do divide on both sides. By 30 here, we get x is 29 over 30. Okay? And so we can see that now, that very last equation, it's easy for us to see that 29 over 30 is a solution. Okay? Now, I think they mentioned this in the video, but I want to reiterate. And one of the things that we're trying to do in Math 136 is get comfortable with fractions, get comfortable with numerical expressions, namely fractions and things involving roots that you maybe aren't comfortable with today. So it's okay if you're not comfortable with fractions today, but one of your goals is to get comfortable with fractions. And one of the ways that we kind of force you to get comfortable with them is we tell you that you have to give us the exact answer. Okay? So if you type in 29 over 30 into your calculator, let me do that real quick. 29 divided by 30. So you get 29 over 30. There's a decimal approximation for it, 0.966 repeating. If you wanted to, I guess this is an equal sign if I'm going to go ahead and do the repeating business, which is approximately 0.9667. I'll say round it to 4 decimals. Okay. Now, all right. When we ask you for an exact answer for this particular problem, this fraction or any equivalent fraction are the only acceptable answers. Okay. First off, 0.9667 is not correct because it's not it's not the exact number. Okay. And B, even though technically this expression is an exact answer, that's also not going to get you any credit. Okay. Again, this is one of these problems where we ask you for the exact answer when really we just say, all right, we just want the rational expression. Okay. So the repeating decimals, anything you may have learned about writing repeating decimals, that's not going to be given. We're not going to give credit for that in this class. Okay. We want you to get comfortable working with fractions. All right. If you have any questions about that, or need further convincing, let me know. I'll try to answer your questions and address your concerns. Okay, so notice here that, going one last thing about this problem. At this step here, this is after we performed a bunch of operations that preserved the equivalence of all the equations. We have their textbook linear equation. Okay. So our original equation, the one that we started with, we're going to say that it is a linear equation. Even though it looked like it might have been quadratic, we're going to say that it is a linear equation because it's equivalent. It's equivalent to a linear equation. Now, some of the more challenging problems in this section involve solving rational equations, or things that look like rational equations. Okay? And so an example of a rational equation that we might want to solve. So we want to solve, where am I here? 7x plus 2 divided by 14x minus 3 is equal to x minus 8 all over 2x plus 3. Again, this is an example. Well, I mean, I would call this a rational equation. I would call this a rational equation. I mean, we're going to be able to, because I don't think it's equivalent. I don't think it's equivalent to a linear equation because of that domain issue. Remember, I got beef with your textbook's definition of equivalent equations. I'd like for my equations to have the same domain. Okay. So, anyways, I don't think that this is. I don't think that this is equivalent to a linear equation, because linear equations, the domain of a linear equation is all real numbers, and here there are a couple numbers that I'm not allowed to use. Okay, namely, I don't want 14 if I have 14x minus 3 is equal to 0. We don't want that, and so we don't want, let's see, 14x is not the same as 3, so x is not 3/14. And similarly, we don't want 2x plus 3 to be 0, and so we don't want x to be, what is that, negative 3/2. Okay, so the domain of this equation is not going to be the same as any linear equation because, again, there are no restrictions for a true linear equation, in my opinion. Now, the strategy here is to cross multiply. And I want to just talk for a minute about why this cross multiply works. Come on, man. Okay, so we're going to talk about an equation of the form a over b is equal to c over d. Now we get an equivalent equation if I multiply on both sides by bd. Now we're assuming that b and d are non-zero, and I can multiply on both sides of this equation by the same number and have an equivalent equation. And so when I do that, a over b times b over d is equal to c over d times bd. And there's some cancellation. Over here I got some b's that cancel. Over here I got some d's that cancel. And the final equivalent equation is AD is equal to CB, like we knew. All right, that's what you get when you cross multiply, right? I think the thing is I'm not convinced that most students understand why cross multiply works or when to use it. I think I may have mentioned in your class, in one of my classes, I can't remember, I had a student that suggested that we do some cross multiplication when there wasn't an equation. Okay, the idea here is there's an equation, and we can cross multiplying is effectively multiplying on both sides of the equation by the same number. Okay, so again, there's some conceptual stuff that goes along with this cross multiply business, and trying to understand when it works and why it works, I think is A, it's not too hard, and B, it helps you understand when a process is available and useful. All right, so anyways, this process is available and useful for this particular rational equation. If I cross multiply, I end up with 7x plus 2 times 2x plus 3 is equal to 8 minus x times 14x minus 3. Again, I don't think that these two equations are equivalent because we changed the domains. Okay? That's why in the videos, they do a good job in the videos of warning you guys that, okay, when you're solving your rational equations by cross multiplying, you have to check that the numbers don't make the denominator zeros. It's specifically so that we can deal with the domain issue. Okay? Anyways, we will go ahead and do algebra. Now we're going to produce a sequence of equivalent equations here by doing some algebra. When I FOIL out, I have 14x squared. I have 21x plus 4x gives me plus 25x plus 6 is equal to, again, foiling out, 14x squared. I have a negative 3x, and 8 times 14. What's 8 times 14? Got to get my calculator out here. 8 times 14 is 112. So negative 112. Negative 112 minus 3 is negative 115. And then negative 8 times negative 3 is positive 24. All right, so that's what we get when we FOIL out both sides. Now I'm going to bring all of my x terms to the left-hand side. Okay, so I'm going to subtract 14x from both sides, and actually both 14x squareds are going to go away. And I'm going to add 115x to both sides, and then I'm going to subtract 6 from both sides. So 24 minus 6. When I add 115 and 25 together, I get 140. 24 minus 6 is 18. So x is 18 over 140. Now this rational expression can be reduced. I can cancel a 2 out, get 9 over 70. But then that fraction cannot be reduced any further. So you should always reduce fractions to their least terms by canceling any common factors. But we want an exact answer here. I mean, some problems are going to specifically ask you for an approximation. And so when they do ask you to approximate to 3 decimal places or whatever, yeah, go for it. Punch buttons on a calculator. But here you want to just reduce the fraction. Now your calculators all have buttons that allow you to reduce fractions. I'll go ahead and let you guys explore your calculators to find out how to reduce that fraction without thinking too hard, or how to turn the reducing of the fraction into a calculator button pressing task. All right, so my answer to I guess this was a linear equation. This was a linear equation. The answer to the linear equation is 9 over 70. And see, the videos do a good job of remembering to check. I always forget myself, but you don't want to. 9 over 70 is not either one of these two forbidden numbers. Okay? All right, so the cross-multiply process is something that can work for a rational equation. Another rational equation that I think this one might actually be in the videos. Yeah, I'm pretty sure this one's in the videos, and they do a specific thing. I'm going to do something slightly different because it's going to be helpful for us here in a couple weeks. So 1 over x minus 2, plus I get to illustrate an important idea about rational expressions. 1 over x plus 2 is equal to 4 over x squared minus 4. Now, for the purposes of finding a common denominator, I'm going to go ahead and factor the denominator on the right-hand side there. So x squared minus 4 is a difference of squares. It factors in x minus 2 times x plus 2. Now in the video, the way that they solve this in the video is they multiply on both sides by the least common denominator, which is x minus 2 times x plus 2. So let's just go ahead and work through that real quick and see what that looks like. When I multiply on the left-hand side and distribute, I have x minus 2 times x minus 2, sorry, 1 over x minus 2 times x minus 2 times x plus 2, plus 1 over x plus 2 times x minus 2 times x plus 2 is equal to 4 over x minus 2 times x plus 2 times x minus 2 times x plus 2. Lots of things cancel. X plus 2's cancel there, x minus 2's cancel there, and you're left with x plus 2 is x plus 2 plus x minus 2 is equal to 4, which is the same as 2x is equal to 4. My plus 2 and my minus 2 cancel here. which is equivalent to x is equal to 2. Now here's a perfect example of, well, x equals 2 is not, 2 is a solution to x equals 2. Okay? 2 is not a solution up here because the equation, 2 is not in the domain of our original equation. Okay? So the fact that actually this equation here, and this equation here have different solutions tells you that they're not equivalent. Okay? They also have different domains. Anyways, x minus 2 doesn't work in the original equation, and so we're going to go ahead and say, well, that's not a solution. Not a solution. In fact, our original equation has no solutions. Okay, so I think that's roughly the process that the video took. You know, multiplying on both sides of the equation by a common denominator. Another way to approach this that doesn't involve changing the domain. That's what I want to show. That's what I want to show you guys. Okay? So let's go ahead and get our original equation back here. 1 over x minus 2 plus 1 over x plus 2 is equal to 4 over, I'm going to just go ahead and write it in factored form, x minus 2 times x plus 2. All right. Now, I just lost my train of thought. Okay. I want to avoid multiplying on both sides by something that might be 0. I guess that's where we ran into trouble here. Remember, one of the things that you can do to preserve the equivalence of equations is to multiply by non-zero numbers or non-zero expressions, and x minus 2 times x plus 2 can be 0. So that's kind of where things kind of broke here. Okay? And so if we can avoid multiplying, that's great. And we're going to have, when we go to solve some inequalities later on, we really need to avoid multiplying by variable expressions. So what we can do is do some arithmetic, do some rational arithmetic here. Okay? I can get common denominators. All right? If I multiply on top and bottom by x plus 2 here, and on top and bottom by x plus 1 here, I can get some common denominators, and I have x plus, ooh, not x plus, man, I'm making some really bad mistakes here. Sorry about this. I want to multiply on top and bottom by x minus 2 here. We have x plus 2 over x plus 2 times x minus 2 plus x minus 2 all over x plus 2 times x minus 2 is equal to 4 over x minus 2 times x plus 2. And then now that these two fractions have the same denominators, I can add them together. That's just rational or addition of fractions, x plus 2 plus x minus 2 all over x plus 2 times x minus 2 is equal to 4 over x minus 2 times x plus 2. And then when I simplify my numerator, I get 2x over x plus 2 times x minus 2 is equal to 4 over x plus 2 times x minus 2. Then if I subtract the 4 over x minus 2 from both sides and simplify, I get 2x minus 4 all over x plus 2 times x minus 2 is equal to 0. And we can maybe avoid making this domain error by reducing the fraction. Okay, I can factor out a 2. Is equal to 0. And I can cancel the x minus 2's. And so I have a rational expression is equal to 0. Okay. Now here, if I want to preserve some equivalence of statements, I might have to say and x is not equal to 2. All right. Keep track of whenever you cancel some denominators, keep track of it. I want to say that it shouldn't cause any difference. I mean, the domains, I guess if I'm going to stick with my guns about these domains of equations being the same, I should just stick to my guns. So these aren't equivalent equations, but they are going to have the same solutions. Okay. Anyways, I have a fraction is equal to 0. And a fraction is only equal to 0 when its numerator is 0. So let me write this down. A over b equals 0 if and only if a is equal to 0 and b is not 0. Okay? So that's a big rule. That's a big rule that we need to kind of keep in the back of our minds. All right, a fraction is 0 only when the numerator is 0 and the denominator is non-zero. So in this particular case, we can see that our numerator is never going to be 0. Our numerator is 2. It's never going to be 0. So here we can see that there are no solutions. So this process, by the way, you don't have to do this process. I just wanted to illustrate this process because, again, it is going to be an important process when we go to solve inequalities. Not necessarily solving equations, but solving inequalities. You run into trouble when you multiply on both sides of an inequality. We'll cross that bridge when we get to it. Okay? All right, so there's an alternative strategy for solving some rational equations. The big idea is, again, just do some rational arithmetic, and the rest is fairly straightforward. All right. Now there are a few kinds of problems from section 2.1 that aren't addressed in the videos, and we can talk about in the context of an example here. Solve S is equal to 2 times LW plus HW plus HL for H. Okay? Now this is, I guess another way to describe this is to isolate H. Again, that means get H by itself on one side and all the other variables and numerical stuff on the other side. Another way of stating this is to say express H in terms of all the other variables, S, L, and W. Okay? Now this particular equation is linear in H. And so we're going to be able to isolate H. Let's go ahead and do that. Now there's a few different ways that we could do that. Like you might be tempted to divide by 2 on both sides right away, but I'm going to go ahead and do something different. I'm going to distribute the 2. We have 2LW plus 2HW plus 2HL. I'm going to leave all of my terms with H on one side and get everything over to the other side. So I'm going to subtract 2LW from both sides. Now here I have 2 terms, and those terms share a common factor of H, so I can factor out the H times 2W plus 2L. And then I can divide on both sides. I have H times 2W plus 2L, and so I can divide on both sides by that term. and get S minus 2LW, come on now, divided by 2W plus 2L is equal to H. And so here I've successfully isolated the variable H. I've solved the equation for H. I don't like that terminology. By the way, here's an example of they're using the word solve to mean something different than find solutions. Okay, so here's an example of you want to understand the language of math. Here the word solve means something different than it's meant for has meant all night. Okay. By the way, this particular equation, if you have a rectangular box, oh god, let's see if I can get a rectangular box drawn here. A halfway decent drawer on the chalkboard and on paper. This is going pretty well. Oh yeah, that's going really well. Okay, so if you have a rectangular box, it's got a height and a width and a length. And so if we have a cardboard box with a top, S here, S equals 2 times length times width plus height times width plus height times length. Well, height times width is the area of the front as well as the back. All right, so 2 times height times width gives us the area of those sides. Let's see, width times length, that would be the top here as well as the bottom part. Okay, so length times width would be the area of the top and the bottom. Height times length would be that side and this side back here. So 2 times height times length would be those areas. This gives us the surface area of this box. Okay, that's what this formula gives you. Okay. One more of these. I know you guys love some subscripts, so I want to do a problem with some subscripts. Solve 1 over r is equal to 1 over r sub 1 plus 1 over r sub 2 plus 1 over r sub 3 for r sub 2. Okay, now just to get an idea about what this is, I'll tell you what this formula is. Those of you who are engineering majors, you might run into this later on. If you have a circuit that has 3 resistors, I can't remember. Actually, I might be off on this. Ugh. I should have looked this up beforehand. I think this is if you have, they call this resistors in parallel. R3. So we got a circuit here that kind of splits into 3 branches and then comes back to 1, and each of the branches has a certain resistance. Then the resistance of the total circuit is given by this equation. Okay, so that's the meaning of all the variables here. I think it's when you have the resistors in parallel as opposed to if you have them all in line. I'll have to go look that up. Anyways, that's what this is all about. Here we have a rational. This is a rational equation in all 3 of these variables, or all 4 of these variables. There's 4 variables in this equation. We got r. We have 4 different r's. We have R1, R2, R3, and then the R that doesn't have a subscript. Okay, the total resistance in this case. Now you might be tempted to just flip all the fractions, but that doesn't work. Okay, that would be a freshman's dream. That would be an example of a freshman's dream mistake. Okay, I don't want to necessarily get into why it's a freshman's dream. We'll go ahead and use the video. We'll go ahead and use the video strategy and multiply by a least common denominator of both sides. In this case, the least common denominator of all the rational expressions is just r times R1 times R2 times R3. Okay? So we're going to multiply on both sides, which has the effect of multiplying every term by that. Okay? So let's do that. We have R times R1 times R2 times R3 times 1 over R. There's my left-hand side is equal to R, R1, R2, R3 times 1 over R1 plus R times R1 times R2 times R3 times 1 over R2. And finally, R times R1 times R2 times R3 times 1 over R3. And there's lots of cancellation that happens. I can cancel an R here, an R1 there, an R2 there, and an R3 there. And we're left with, let's see, R1, R2, R3 is equal to R, R2, R3 plus R, R1, R2 plus R, R1, R2. Ugh. Okay, now we're trying to solve for R2 here. And so I think what we want to do is get every term that has an R2 in it on one side and everything else on the other. And so I'm actually going to bring all my R2 terms over to, well, no, actually I take it back. I take it back. I'm just going to bring all my R2 terms over to the left-hand side. Okay? So I have R1, R2, R3 minus R, R2, R3 minus R, R1, R2 is equal to R, R1, R3. This is supposed to be R3. That was... No. This one was supposed to be R3. Why aren't you guys catching me on this? This one... Sorry. That one legitimately is R2. Sorry about that. All right. But that meant I have to take... Man, I butchered this. I'm so sorry. I want this one to go over. And that one's going to stay... This one's going to stay put. We wanted only the terms with R2s. Okay. That should be right. Sorry I totally screwed that up. This one's a little bit more challenging than anything you guys have to worry about on quizzes or tests, but I wanted to go ahead and use it as an opportunity to kind of strengthen our variable skills, but in the process I completely butchered it. Anyways, on the left-hand side now, I have three terms separated by minus signs, and they each have an R2. That was kind of the point. And I can factor out that R2. So we have R2 times R1, R3 minus R, R3 minus R, R1 is equal to R, R1, R3. And so if I divide on both sides by the non-R2 part, the non-R2 factor of that left-hand side, I get R2 is equal to, I'm going to write in my denominator first, R1, R3 minus R, R3 minus R, R1, all under R times R1 times R3. Okay, that was fun, wasn't it? All right, so there's another example of solving for a given variable, or again, that's the same as isolating the given variable or expressing the given variable in terms of the other variables. All right. I think now's a good time for a break. It's nice since nice is I'm not trying to say anything, but with me not having a class sit in front of me, I'm able to go through this material a little bit faster than I normally would. So I'm going to go ahead and take a 5-minute break at this point, and then I'll come back and talk about what am I going to talk about when I come back? Section 2.2, which is story problems. So 5-minute break. If anybody happens to be watching right now, it says I have one watcher. I don't know if I count as a watcher, if there's someone legitimately watching. I'll be back at 7:25. Okay, I'm back. So yeah, that we talked a lot about concepts there in that first bit as they're related to equations. I made it a little bit harder than it needs to be, but hopefully that's going to pay off here at the end of the night as well as next week. Okay. Anyways, the second part of our class is about section, what is it? 1.2, which is applied problems. Sorry, 2.2. So we got section 2.2, which applied problems. I don't know if it happens before this, or typically that's the code word. Applied problems or applications, that's the code word for story problems. We're going to take the mathematics that we've learned and apply it to real world situations. Now most textbooks, ours included, have some strategies for dealing with applications or applied problems. Here's our textbook's guidelines for solving applied problems. The gal who presented the story problems in the Math 136 YouTube channel videos, she had a slightly different list of things, and her list is just as good as this one. But let's go ahead and just read through this real quick. It says, if the problem is stated in writing, I mean, that's the point. Well, I guess some story problems maybe don't come with any words, they just have pictures. But those are very, very rare. Okay? So if the problem is stated in writing, it's like, all right, like 99.99% of the time, an application problem is going to be stated in writing. Okay? So you want to read it carefully. I don't know about several times. Make sure you read it carefully enough to where you kind of get the gist of the story. Okay? The key thing is that you want to identify the unknown quantity or quantities that you're supposed to be finding. You know, you want to find, there's usually one question or one sentence that's typically towards the end of the story that tells you what you're supposed to find. Okay? Here it says the phrases containing words such as what, find, how much, how far, when. Those are going to identify the quantity that you're supposed to find. And then step 2, they say, okay, introduce a variable. Introduce a variable to denote that unknown quantity. When appropriate, draw a picture and give it labels. Actually, I don't know if any of the problems I have require pictures, but definitely if you have problems where they're describing some geometric thing, you want to draw a picture. I know in my trig class where we're talking lots about triangles and circles and things like that, you definitely want to draw some pictures. In the context of the story, like I said, there's usually one sentence that describes what you're trying to find. All the other sentences are describing the other aspects of the story, the other facts, okay? And you want to list those facts. You want to try to express those facts. They say here as relationships, and they say a relationship may be described by an equation. And that's, I guess, the idea here is that you're translating the facts of the story into mathematical equations. Okay? And that also goes with step 5. After analyzing the list in guideline 4, formulate an equation that describes precisely what is stated in words. Then in step 6, you're supposed to solve an equation. And then step 7, check that the solution obtained in 6 is a solution to the statement of the problem. Okay? Now, I usually describe this as there's like 3 components. The first big chunk here, the hard part is steps 1 through 5. Okay? Steps 1 through 5 are in these guidelines. Again, depending on whose guidelines you read, you're going to have different guidelines. But I see regardless of what a person's guidelines are, they're typically broken up into 3 steps, okay, as I see it. The first step being translate the story into a boring math problem. And in the context of a math class, when you learn a new kind of problem, there's usually some story problems that allow you to practice that problem. So we just got done talking about a section where we were solving equations. And so all of our stories we're going to be able to translate into linear equations, basically, or equations that are equivalent to linear equations. You know, when you study, you know, those who move on to a calculus class, for instance, one of the things that you're going to study is derivatives, okay? And talk about rates of change. And so you want to translate your story into something where you have to find derivatives, okay? Anyways, the point is that you're able to translate the words of the story into a boring math problem that looks like solve this equation, okay? The second step is to do the boring math problem. And for us, it's going to be solving equations. And then the third step is translate the answer to the boring math problem back to something that makes sense in the context of the story. Okay? All right, so those are going to be the rough steps that I follow. Okay? Okay, so let's do some problems here. I sent you guys a message on Ivy Learn where all these stories came as an attachment. So if you're watching this after the fact, go print that out if you need to, or just refer to it. You know, you don't have to copy down all the words of the problem. Just copy down, hey, this was story problem number 1, and then if you need to, go look at the handout. Okay. All right, so this first one's about pre-sale prices. A clothing store holding a clearance sale advertises that all prices have been discounted 20%. If a shirt is on sale for $28, what was its pre-sale price? Okay, so here I guess if we're following something that roughly looks like the books, we've read our story carefully. We have a rough idea based on personal experience of what's going on with this in terms of, all right, $28 is the sales price of a shirt. The pre-sale price is going to be something that's more than $28. Okay, they're asking what was its pre-sale price, so that's the unknown quantity, and so we want to give that quantity a variable amount, or variable, assign a variable to that quantity. I'm going to go ahead and call it P. P is the pre-sale price. You can call whatever you want. If you'd rather call it X, that's fine. Pre-sale price. Okay. Now I'm going to go ahead and also assign a variable to the sales price. Okay. And for this particular store, where everything's been discounted 20%, no matter what object we're talking about, the sales price is you're gonna take your pre-sale price and you're gonna subtract 20% of the pre-sale price, or you can write it as the pre-sale price times 1 minus 0.2, or you can write it as 80% of the pre-sale price. Okay, so our sales price is going to be 80% of the pre-sale price. Now they also told us in the story that the sales price was $28. Okay, so we can put that value in for S. And now I have a linear equation. I have a linear equation in P, and I can solve it. Okay, if I divide on both sides by 80, I get P is 28 divided by 0.80, which I believe should be 35. So 35 is the numerical answer to my boring math problem. Here my boring math problem is solve that equation. Solve that linear equation, which was a pretty easy linear equation to solve. Okay? Anyways, the answer to my boring math problem is 35. In the context of the story now, this is where we translate back to the answer for the story. P was a pre-sale price, and so the shirt, it was a shirt, right? Yeah, shirt originally cost, it's supposed to be an N, $35. Which is a reasonable amount for a shirt, I guess. Definitely for a shirt that costs $28 on sale. Remember, we wanted to make sure that our answer was more than 28. So you can always, at the end of a story prop, you should always do what I call a reality check. All right, does the answer that I came up with roughly match my idea of what it should have been? And that's something that you can think about ahead of time. Okay. All right, so that one wasn't too bad. That one wasn't too bad at all. Moving on to number 2. A consulting engineer's time is billed at $60 per hour, and her assistance is billed at $20 per hour. A customer received a bill for $580 for a certain job. If the assistant worked 5 hours less than the engineer, how much time did each bill on the job? Okay, the key sentence here is how much time did each bill? Okay, so we have 2 unknowns here. 2 unknowns. Now, in the videos, she used some, I guess, she used some interesting strategies for solving systems of linear equations. And those of you who haven't seen systems of equations, that might have been spooky. We don't need systems of equations. Okay, we don't. She was using the elimination method in a couple of problems. And if that was confusing to you, that's okay. You don't need to do your problems that way. All right, let's go ahead and think about how we can get the job done without doing anything super duper fancy here. All right, the point here is we have 2 variables. I'm just gonna use X and Y. X is the time billed by the engineer, and Y will be the time billed by her assistant. Okay? Now, there's a relationship between these 2 variables. So the assistant worked 5 hours less than the engineer. So the time worked by the assistant, the time worked and the time billed should be the same amount here. The time billed by the assistant will be 5 less than the time billed by the engineer. That's X minus 5. 5 less than kind of translates into subtract 5 from. Okay? So we don't really need this second variable. Okay? But we're going to go ahead and keep it to kind of make our task a little bit easier. Now, the customer received a bill for $580. Okay, so the total bill, that was $580. That's what you get when you, so that's the result of adding the engineer's bill. I'm just going to abbreviate here. Engineer's bill plus the assistant bill. Right? If you take the amount billed by the engineer plus the amount billed by the assistant, that gives you the total bill. The amount that's billed by the engineer, well, we'll take her time, X, times her rate. Okay? She bills at $60 an hour. And the assistant's bill is the assistant's time times the assistant's rate, $20 an hour. Okay, now if I clean this up a little bit, I got 580 is equal to 60x plus 20y, and then using the fact that we actually have an expression for y in terms of x, that allows us to get 580 is 60x plus 20 times x minus 5. Okay, there's our boring math problem. Solve 580 is equal to 60x plus 20 times x minus 5. So we have a linear equation to solve here. Let's get rid of our parentheses here. 60x plus 20x minus 100 when I distribute the 20. If I add 100 to both sides, I get 680 is equal to 80x. And then if I divide on both sides by 80, we get x is equal to 680 divided by 80. And I get 680 divided by 80. Oops. I get 8.5 hours. Now, in the context of this particular problem, well, sorry. See, I already did that last step. I got x is equal to 8.5. Now, I'm comfortable using a decimal. This is an exact decimal right now, as opposed to writing this as, I think this would be 17/2. I'm comfortable using a decimal here because when I go to translate this back to an answer to the story, how much time did each bill on the job? I'm comfortable saying that, all right, the engineer billed 8.5 hours, because that's kind of how you usually represent the time that you work, 8.5 hours. You wouldn't represent it as 17/2 hours, okay? As math students, we're comfortable with 17/2, but when it goes to reporting, it's 8.5 hours, okay? And then the assistant billed 5 hours left, so when I subtract 5 from this, I get 3.5 hours. And then we can go back and check if we wanted to. It's always a good step to check. 8.5 times 60 hours plus 3.5 times 20 hours. We do that on my calculator. 8.5 times 60 plus 3.5 times 20. That does give me the $580 that was billed. Okay, so it's always a good idea to check your answer when you have time. That's not my answer. This is my answer. There we go. So see here we had, I think that again the videos may have presented these doing a system of equations kind of thing, and we don't necessarily have to deal with systems of equations. Number 3, about drug concentration. Theophylline, which is an asthma medication, is to be prepared from an elixir with a drug concentration of 5 milligrams per milliliter in a cherry-flavored syrup that is to be added to hide the taste of the drug. How much of each should be used to prepare 100 milliliters of solution with a drug concentration of 2 milligrams per milliliter? All right, so here's a perfect example of if you try to figure out what the answer is to the story, or even figure out what the answer looks like to the story just on a first read of the story, that can be very challenging. So let's go ahead and try to find the problem statement here. How much of each should be used? And in this, each is, there's a cherry flavored syrup and there is an elixir. So I'm going to use E. Is going to be milliliters of elixir. And I know that it's milliliters because they're going to end up being, when I combine them, they're going to combine to be 100 milliliters, okay? And I'm going to use C to be the milliliters of cherry syrup. It's always fun, fun is maybe a strong word. It's always good to use variables that are meaningful. Like in the last problem we had X and Y. Yeah, X and Y are easy to work with, but E and C, I'm going to remember that there's a story. I'm going to remember that there's a story at the end, okay? Now, milliliters of elixir. Now we just said one of these two, we're going to prepare 100 milliliters of solution. So the relationship between these two variables is if I take the milliliters of elixir plus the milliliters of syrup, I should get 100 milliliters total. All right, so this is going to be the equation that we're going to use to get around a system of equations. Now, if we were doing a system of equations, that would be one of the equations, but this is going to be the equation that we use to get around having to deal with a system. All right, now the second part of this setup is we want to, the other part of this is I want my 100 milliliters to have a certain concentration. 200 milligrams per milliliter, okay? So the total drug content. That's going to be the next thing, okay? If I take the 2 milligrams per milliliter of concentration times the 100 milliliters of solution, you get that there's going to be 200 milligrams of the drug in the mixture. Okay? Now, so this is going to be in the mixture. If I want to know how much of the drug comes from the elixir, well, the elixir has a concentration of 5 milligrams per milliliter, and I'm putting in E milliliters of the elixir. So that's going to be 5E milligrams from the elixir. And then from the syrup, well, the syrup has no milligrams. 0 milligrams from syrup. That's just there for the cherry flavor. Okay? So, turns out that C, now these, I guess the idea here is that, all right, if I take the drug from the elixir plus the amount of drug from the syrup, that should give us the total amount of drug in the mixture, right? This is drug from elixir right here. The amount of drug that comes from the elixir plus the amount of the drug that comes from the syrup should be the total amount of drug that's in the mixture. And that tells us that, oh, 5E should be 20. So here's our boring math problem. Solve 5E is equal to 20. Sorry, 5E is equal to 200. And here's where you'll get, okay, the amount of elixir is 200 divided by 5, which is 40. And then remembering that this came from a story, they want to know how much of each should I have, okay? So if E and C have to add up to 100 and E is 40, that must mean that C is 60. All right, so there are 40 milliliters of elixir and 60 milliliters of syrup. Now this is an example of a mixture problem. I think the videos did an example of a mixture problem where you're mixing eye drops or something like that. I can't remember the exact context, but this is a classic mixture problem. Actually, the previous problem was another mixture problem, right? Instead of mixing chemicals or drugs, we were mixing engineer hours and assistant hours. So this was a mixture problem. And when you're able to kind of identify a class of problems, then you can start to understand how their answers are the same. Okay, so here when we went to set up our equation, we had the total amount is the amount from the engineer, which is the engineer's rate times their time, plus the amount from the assistant, which is the assistant's rate times their time. Over here, the total drug content would be, all right, the elixir's rate times its amount plus the syrup's rate, which happened to be 0 here. And I guess we could have put the 0 times C if we wanted to. The syrup's rate times its amount. Okay, so both of those are mixture problems. This last one was the classic mixture problem, whereas there are a couple of other problems in the videos as well as on your homework that you can identify as mixture problems, and you can start to approach those problems with comparable strategies. Okay. This last one, this is one that the video didn't do anything similar to, and my students last semester had difficulty with this kind of problem. There's actually 2 problems similar to this one on your homework. One of them involves a boy and a girl delivering newspapers, I think. And the other one involves either pumping some water out of a pool or pumping some water into a pool. It had some pumping going on. Okay. Anyways, I would characterize these are other mixture problems, the way that I kind of think about them, or you can think about them as work problems. So let's look at read the story first, and then talk about classifying it. It says, it takes a boy 90 minutes to mow the lawn. His sister can mow it in 60 minutes. How long would it take them to mow the lawn if they worked together using 2 lawn mowers? So again, I think of these as a work mixture problems, in the sense that I'm mixing the boys mowing with the girls mowing, and they're trying to accomplish a task. That's where the work part is coming into play. Okay, so in the whether you're pumping water into a pool or pumping water out of a pool, you're trying to accomplish a task. Okay, and there's a mixture of a couple different kinds of hoses. Okay. All right, now there's kind of 2 ways to approach it, and I want to present both ways. The book's way to approach this is to focus on rates. Okay. It says that in this case we got a boy and a girl that are mowing. It says the boy's rate plus the girl's rate, there should be an apostrophe here, the girl's rate is the same as their combined rate. Okay. The idea being that, okay, the boy gets 1 lawn per 90 minutes, and the girl's rate is 1 lawn per 60 minutes. Should be an E in minutes. The combined rate would be, all right, 1 lawn in some unknown number of minutes. Okay. Now I guess here, how long? Okay, so T is the how long, the answer to how long. Okay. The time worked by the pair. Now there's one minor piece of confusion. The boy and the girl are not going to mow the same amount. They're going to mow for the same length of time. They're both going to mow for T minutes. But since they work at different rates, one's going to do more work than the other. Okay? So this isn't as simple as saying, all right, well, if it takes the boy 90 minutes to mow a full lawn, then it's going to take the boy 45 minutes to mow half a lawn and the girl 30 minutes. And so the girl's going to mow for 30 minutes and the boy's going to mow for 45 minutes. That's not how it's going to work. All right, the girl's going to get done with her half the yard in 30 minutes, and then she's going to keep mowing. She's going to mow part of the boys' yard, and they're going to get together. They're going to finish in some time less than 45 minutes, right? The boy's not going to have to mow an entire half of a lawn, so the boy's not going to end up spending 45 minutes mowing. All right, anyways, if we look at this equation, without all the units involved, it's a rational equation. 1 over 90 plus 1 over 60 is 1 over t. Okay. Let's just go ahead and I'm just going to go ahead and add these two fractions on my calculator. 1 divided by 90 plus 1 divided by 60, and my calculator gives me a decimal answer, and I'm going to use my calculator to spit back 1 over 36 is equal to t. Sorry, 1 over t. And then when I cross multiply, I get t is equal to 36. Okay? Now, like I said, this is our book strategy, and if you can identify this as a work mixture problem, or just a work problem, or a problem where we're getting a task done with two different people or two different things working on it, and you can remember this setup, then that's not a terrible way to get the problem done. Okay? By the way, we kind of talked about, all right, if we had two girls working, it would take them 30 minutes. And if we had two boys working, it would take them 45 minutes. And so with one boy and one girl, we're expecting that it should take some amount of time between 30 and 45 minutes, right? And the fact that our answer is between 30 and 45 minutes, that's a good reality check here. Okay, here's how I deal with it, and again, why I think of this as a mixture problem. All right, I'm thinking about this in terms of if you focus, instead of focusing on rates, you focus on work done. Okay, again, T is the time that they spend working. That's probably a better, or time spent mowing. Okay, now there still are rates. Okay, the boy still works at a rate of 1 over 90, and he's going to work for t minutes. All right, so this is the work that the boy gets done. The girl's going to work at a rate of 1 over 60. She mows one lawn per 60 minutes, and she's also going to work for t minutes. And so this is the work done by the girl. Girl, come on, man. I turn into like a dyslexic dude when I'm writing on the board. Not that there's anything, I mean, that came out wrong. I don't mean to demean anybody who actually has dyslexia. Now, their combined work is they get one lawn done. Okay? They get one lawn done. And so the equation is slightly different. The idea is slightly different. But I find this way easier to think about the problem. Also, I think one of the reasons why I prefer this second method is if it turns out that, all right, the boy showed up late and he worked for 5 minutes less than the girl, then we can easily modify this version to say, okay, t minus 5. T is the time spent working by the girl. And all of a sudden, it's really easy to modify this to slightly different stories or slightly more complicated stories. Okay? But at the end of the day, with these work problems, you can set them up either way you want. If you prefer focusing on the rates combining to be one rate, or here again, I think of combining the amount of work they each got done into, all right, it should combine to getting one task done, in this case, one lawn mowed. However you find it easiest to work with. Anyways, this turns into 1 over 36. T is equal to 1. So again, we get T is equal to 36 minutes. So anyways, again, there's a couple of different ways of thinking about this problem. I always find it's good to have, if you can, have more than one way of thinking about a problem. It's always beneficial. All right, so I think that's all of the story problems that I had. You have several story problems in your homework to look at. Again, Chris, I think, is the teacher who did the video. She went through several examples in the video as well. When it comes down to it, try to have some kind of process. Whether or not you stick to your process, whether or not you stick exactly to your process, you don't necessarily have to like rigorously stick to it, but have some kind of process for approaching story problems, so that if you happen to run across one that gives you trouble, then you have some things that you can do. I think that's one of the hardest things with story problems that students have, is just getting started. Okay, give yourself some things to do so that A, you can have a better chance at getting started, and B, when it comes time for me to grade, there'll be some ways to earn some partial credit if you can get some of the early stage, identifying variables, identifying what you need and what you know. I mean, I can give you partial credit for that. If you don't write anything, I can't give you any partial credit. All right, so that leaves us with time to think about what you guys are going to look at for next week. So we're going to get a little bit of a preview for next week's stuff. I don't think I have any. Yeah, I'm just going to go down here. So the videos that you're going to watch before next time are for section 2.3 and 2.4. Okay? So section 2.3 is on quadratic equations. I should just, why abbreviate? I'm not running out of time here. Section 2.3 is on quadratic equations. So again, this is a bit of a preview. Now, the main focus in section 2.1 was on linear equations, and as well as rational equations that were equivalent to linear equations. 2.3 is all about quadratic equations. So quadratic equations are equations of the form ax squared plus bx plus c is equal to 0. So there is an x squared term here that we didn't see with the linear equations. And unlike linear equations where we were able to isolate x, for quadratic equations, isolate x usually doesn't work. Okay, we need other strategies. Sometimes. Okay, and so one thing I want you guys to do when you're watching the videos is to focus on which strategies they're using. Okay, so there are a few. Actually, I think these are the only four that we're going to work with. One involves I taught a class once that referred to this as the square root method. For special quadratics. I think our book calls these special quadratics. Okay, these special quadratics are quadratics of the form x squared minus d is equal to 0, where d is a positive number. I guess it could be 0 too. All right. All right, so let's just do an example here so we can see how that works, so we can maybe not worry about the fact that we don't know what d is. How about x squared minus 7 is equal to 0? All right, so here we can isolate the x squared. And then adding 7 to both sides of these equations. All right, we have 2 equivalent equations here. And you're tempted to take a square root. And this is what the videos do. All right, so actually I'm going to go ahead and put it right here. Okay. And that turns out to preserve the equivalence of the equations. Okay. Because both sides of these equations are positive, this works. Okay. Now, one of the things that the videos don't do is explain the next bit of steps. And here's the next steps. We talked the other day about, all right, the square root of a squared is equal to the absolute value of a if we don't know in general. Okay, so in general, the absolute value of the square root of a squared is the absolute value of a. If we don't know for sure whether or not a is positive or negative, we have to have these absolute values. Okay, and so we have, when I do the absolute value of x squared, when I take the square root of x squared, I get the absolute value of x is equal to 7. Okay, now there's two different ways. There's 2 different ways that the absolute value of a number can be 7. Okay, so either, I can't write all of a sudden. Either x is equal to 7, in which case, because remember the absolute value of a positive number is just itself, or x is equal to -7, because again, the absolute value of -7 is 7. So both of these values, there should be a square root here. I'm getting all kinds of twisted. These red square roots just I did those for y'all's benefit, and it completely destroyed my brain. I can't deal with the colors. So this should be the square root of 7. All right. The point here is that, all right, if I know that the absolute value of a number is the square root of 7, then either the number is the square root of 7 or that number is negative square root of 7. And so that's where you get x is plus or minus the square root of 7. Okay? That's, I guess, how they jump all the way down here. So they skip a few steps, which is fine. Okay? The square root method said, all right, in this other class said, all right, if x squared is equal to d, where d is positive, then x is equal to plus or minus the square root of d. Okay, and you're free to make that straight jump. All right, you don't have to show me any steps. You don't have to deal with this square root of x squared is equal to the absolute value business. You don't have to worry about all this explanation over here. Okay. But I guess the reason why I'm bringing this up is I don't like the video's explanation for this process. Okay? And a lot of students have trouble remembering when do they put the plus minus square root and when do they just have just the square root. The way that I remember it is if you put the square root, I guess let me state it the other way. If the square root's already there, then it's just one number. If you put the square root there, if there wasn't originally a square root, in this problem. If you put a square root there, then that's where you got to do the plus minus business. Okay? Best thing is, all right, the only time I'm going to put any square roots anywhere and put any plus minuses anywhere is if I'm using this square root method for special quadratics. Okay? So anyways, that's one method for solving a certain class of quadratics. Another method involves factoring and use the zero factor property is the name of this strategy. Okay. So for example, if we want to solve x squared minus 3x minus 2 is equal to 0. Now this is not a special quadratic. There's an x term here. Okay? So this business of isolating x is definitely not going to work here. Okay? We could factor the polynomial here. This polynomial factors, that should be a plus 2. Bam. It factors into x minus 2 times x minus 1 is equal to 0. Okay? So we can factor this quadratic. Now here's the zero factor property. It's a property of numbers. I think it should be listed. Well, it's definitely given in your book. Okay? It says if a times b is equal to 0, then either a is 0 or b is 0. Okay? If you got two numbers and they multiply together to give you 0, then at least one of those numbers has to be 0. That's the zero factor property. It is a property of numbers. If any of you have done any matrix multiplication in your Algebra 2 courses in high school, or anybody who took pre-calculus in high school maybe, you might have learned about matrix multiplication. You can multiply two matrices together to get 0 where neither of the matrices are 0. Okay, so that's just for folks who've seen matrices before. The point here is that the zero factor property is a property of numbers, and it's a property about 0. Okay, 0 is the only number where we can say anything. Okay, like if you knew that a times b is equal to 1, then you don't know anything about a or b other than that they're reciprocals. Okay, a and b could literally be any number. Okay, if they multiply to 0, then at least one of them has to be 0. All right, so that is one reason. The zero factor property is one reason why you're going to see us piling everything on one side of an equation and getting 0 on the other. Okay, the zero factor property is the primary reason why we almost always get everything on one side of the equation and 0 on the other. Okay, now the zero factor property in the context of this means, okay, I got two numbers being multiplied together. There's a multiplying going on here, and they give me 0, so one of those numbers has to be 0. Either x minus 2 is 0 or x minus 1 is 0. Okay, and now we've got two linear equations to solve. X is equal to 2 or x is equal to 1. All right, so that's kind of the motivation or the foundation for the strategy or method of factoring defined solutions. Okay, so all right, so far we have a square root method for some quadratics that kind of looks like isolating x. We've got this factoring and using the zero factor property that really, at an initial stages at least, doesn't look anything like isolating x. There are two other methods for solving quadratics. One of those you may have seen before. It's called the quadratic formula. I'll go ahead and write it down. The solutions to ax squared plus bx plus c is equal to 0 are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So there's the formula. You're not meant to have it memorized tonight. If you watch the videos, I'm pretty sure the lady's going to sing you a song. So if you have trouble memorizing this formula, think about singing the song. At the end of the day, though, you're going to be expected to have this formula memorized. Again, not tonight, but definitely by the time you take the first midterm, which is, by the way, not too far away. And then the last method for solving quadratics is called completing the square. Okay? The last method for solving quadratics is called completing the square. And this is more of a process. I guess the quadratic formula is a formula. Completing the square is a process, and it's a pretty challenging process. I'm going to go ahead and let the ladies in the video show you the process. The motivation for the process is what I wanted to show you tonight. Okay. If we were somehow, all right, we're starting with ax squared plus bx plus c is equal to 0. And somehow we want to translate that into an equation that looks like x plus some other number b. I'm using different variables here. Capital B is different than lower b. If I were somehow able to do some voodoo, this, by the way, this is referred to as the standard form. I forgot to mention that before. This is the standard form of a quadratic equation. This second equation here is still a quadratic equation, but it's in a different form. But anyways, the ladies in the video are going to show you the voodoo. If you're able to understand the voodoo about how to transform the standard form into something that looks like this, then we can use the square root method to say that x plus b is plus or minus the square root of c, and then subtract b from both sides to get x is negative b plus or minus the square root of c. Okay, so again, this step right here, this is the completing the square step, and they're going to show you how to do this in the video. Okay, and I want to say that again. They are going to show you how to do this in the video. I'm not going to show you how to do this ever. They're going to show you how to do this in the video. They're going to show you how to do this about 15 times in the video. There's no reason for me to spend any amount of class time showing you guys how to do this complete the square voodoo, because they're going to show you. Okay? So you have to watch the YouTube videos for completing the square. I'm going to do a problem in class next week where I complete the square, but you're not going to like that problem if you haven't watched the videos. I promise you. You're going to be, I think I mentioned on the first day of class, if you guys don't watch the videos, you're not going to like me so much. You are going to absolutely hate my guts next week if you don't watch the ladies complete the square a half a dozen or more times on the videos. Okay? So please, for your benefit and mine, watch the videos where they show you how to complete the square. Okay? Deal? Right on. Okay, so that's all I wanted to say as a preview. Again, that was a preview for section 2.3 on quadratic equations. The other section that you guys are going to learn about, we're going to talk more about next week, and you guys are going to watch some videos about, is section 2.4, which is on complex numbers. And complex, I guess the name here, complex numbers, make them sound scarier than they are. Complex numbers are not nearly as scary as complex fractions, okay, or complex factoring. Complex numbers are actually pretty easy. Again, I want to provide a little bit of motivation for this. Now, on the first night, we kind of started off talking about number systems, and I want to think about those number systems in the context of solving equations. Okay, so if you want to, if you just start with integers, okay, if you want to solve the equation 2x minus 1 is equal to 0, you can't do that with whole numbers. Okay, we need rational numbers. Okay. By the way, we talked on the first night as well about, okay, it's okay to think of rational numbers as fractions, but that's not really what they are. One way that you can define rational numbers is you can say, okay, there's solutions to linear polynomial equations with integer coefficients. Well, I guess we want prime linear polynomial equations with integer coefficients. But that's neither here nor there. I kind of almost wish I hadn't put that down there. Okay. Anyways, if you start with the whole numbers, then it doesn't take you too long to find equations that you can't solve with whole numbers. Okay. Now the solution to this equation is the rational number that's represented by 1 over 2. Then, all right, so now we have the rational numbers. Then when we go to start solving some quadratics, like x squared minus 2 is equal to 0, that's where we need some irrational numbers. The square root of 2 is not a rational number. If you want to go look up a proof that is not rational, I don't think it can be a little bit challenging. If you've never seen, it's a special kind of proof, and if you've never seen it before, it can be a little bit challenging. Okay, but if you're interested in seeing what a proof of the fact that the square root of 2 is not a fraction, what that might look like, you can go ahead and look that up. I'm sure there's somebody on YouTube who's proven that the square root of 2 is irrational. Okay. Anyways, when we go to start solving some quadratic equations, we need some irrational numbers. Okay, and that gets us pretty far. Actually, the technical word is algebraic. Okay, when you want to go solving polynomial equations with integer coefficients, you need the algebraic numbers. Okay. All right, and that gets us. So we need more numbers when we go to solve quadratics. And actually, if we try to solve the quadratic x squared plus 1 is equal to 0, it can't be done with real numbers. Okay. In particular, if a, let me just use x. If x is real, then when you square it, when you multiply it by itself, it's always going to be non-negative, right? It's always going to be non-negative. And if you add 1 to that, then it's always going to be bigger than 1. All right, remember, take any number and multiply by itself, you always get something that's non-negative. Take a positive number times a positive number, it's a positive. A negative times a negative gives you a positive. And 0 times 0 gives you 0. Okay? So this is not something that there are no real solutions to this equation. But if we want there to be solutions, then we have to kind of invent new numbers. And so you can think of every step of the way here where we're trying to solve equations that we don't have numbers for as like inventing new numbers. I don't know that that's the right, I mean, that's not the way that I think about it, but that's not necessarily a wrong way of thinking about it. Is, all right, we're just trying to solve equations. We need new numbers to solve different kinds of equations. And if we want to solve this kind of equation, we have to invent a new number that does things that the real numbers don't. Okay? In particular, we need numbers that, when you square them, give you negative values. Again, this equation here would be equivalent to x squared is equal to -1. Okay? We need to make up a number that when I multiply by itself gives me 1. And we're going to do that. We're going to invent a new number I. I guess I'm going to put this in quotation marks because there's I don't know if it's a debate, but it's an interesting question about, all right, do we invent mathematics or do we discover it? Okay, is math something that man made up, or is math something that exists independently of man that we discover? Okay, and I guess if you want to think about aliens, aliens are probably going to discover some math, and so maybe we didn't make it up. Okay, maybe we're just discovering it the same way that maybe an alien civilization would. But anyways, we're going to invent a new number, and we're going to call it I. A new number, I. That's not a very good I. I usually put a little tail on my I for some reason. There we go, I. Okay, we're going to call this number I, and then this new number has one special property. When I square it, it gives me -1. All right. Now, in a certain sense, you could say that I is the square root of -1. Okay, that's what our book says. I don't necessarily know that I like that, because then what does the square root of -1 mean? We made a big deal about our definition for square roots last week, and square roots, according to our definitions in what section was it, 1.2, square roots are the unique positive number satisfying blah 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 blah. And now we're just talking about the square root of -1, and it's a new number I that's neither positive nor negative. Okay, so I don't necessarily think I like that version of it. This is the important thing for right now. Okay, in my estimation, that's the only property. Now you can use this property to say some other things like, hey, I cubed. If I multiply on both sides by I here, is -I, and I to the 4th is -I squared. But we just talked about I squared is -1, so that's -1, which is 1. So we get I to the 4th is equal to 1. And then I to the 5th is just I then, and I to the 6th is I squared, which is -1. If we could just keep multiplying by I, and there's this cycle. There's this cycle of I, -1, -I, 1, I, -1, -I, 1. So it just cycles. There's 4 stages in the cycle. Okay. All right. Now, when we invent this new number I, we'd like for it to play nicely with all of the other numbers that we have. Okay. So for instance, if I have A is real, if I have a real number A, then we want A times I to be meaningful, to be a number. Okay, so we'd like to take this new number I and multiply it by our other numbers. I guess we already have a -I here, right? We'd like A times I to be a number. And then, I wanted to say B times I. Sorry, if B is real. And if A is real, then we want to be able to add a real number to one of these B times I numbers. So for what it's worth, I think our book has some interesting terminology that's not necessarily consistent with the terminology that is used by mathematicians. But we'll talk more about the terminology next week. I think our book calls these pure imaginary. And it calls numbers that look like this complex. As long as, well, no, it just calls those complex. Okay? So these numbers that look like A plus BI, those are the numbers that are complex numbers. Okay? And what you're going to learn is the arithmetic. Okay? So what you're going to learn by watching the videos is the arithmetic of complex numbers. And it turns out that it's not all that bad. Okay? It turns out that it's not all that bad. You're going to learn how to add them together and subtract them. That's super duper easy. Multiplying them together is not all that bad. Dividing one by the other, that's where things get a little bit challenging, and where we're going to use the idea of conjugates. You guys use the idea of conjugate expressions when you rationalized denominators involving square roots. So this is where we can use that same idea of conjugates to rationalize denominators that have complex things in them. But I'll let you guys go ahead and watch the videos to see how that works. Okay? So that's the second part of next week, where you're going to learn more about complex numbers, and in particular the arithmetic of complex numbers. And yeah. So anyways, that's all I have for tonight, I think. Yep, that's all I have for tonight. If you have any questions about this lesson, please send me a message as soon as you have a question. Otherwise, I will see you in class next Monday, where we will talk more about solving quadratic equations and working with complex numbers. And we'll also, our first test is just 2 weeks away. So we'll also talk a little bit about the first midterm exam. So I will see you guys next week. Thanks for watching.